Hi everyone, my name is Chad. I've been doing research on pure B filtering with a convolutional neural network with Dr. Colin Bischoff as my advisor. In the early universe, an opaque fog of hot ionized gas existed. Photons couldn't freely travel without scattering. But as the universe expanded and cooled, neutral atoms formed and the photons could then travel freely throughout the universe. These photons scattered for the last time as the ionized plasma transitioned to neutral gas. The light traveling from this moment is seen today as the cosmic microwave background. A fraction of these photons were polarized due to Thomson scattering. And why do research on polarization? Well, the theory of inflation explains that the universe expanded extremely rapidly in a fraction of a second after the Big Bang. A consequence of the theory leads to the prediction of a background of gravitational waves in the early universe. The gravitational waves are faint now and cannot be directly observed, but we may indirectly observe gravitational waves by studying the mark they left on the cosmic microwave background in the form of polarization patterns. There are two types of polarization of concern: E-mode and B-mode polarization. Density or scalar perturbations only generate a specific polarization pattern, E-modes seen on the left. The CMB is dominated by mostly E-modes. Gravitational waves create both E and B modes, so detecting B modes would give observational evidence that in the early universe, a background of gravitational waves was present. Models of inflation predict these B modes will be present at angular scales of about a degree or higher. We can see in this picture below that the polarization is shown by headless vector arrows across a horizontal wave vector k. The polarization of E modes are parallel or perpendicular to the wave vector, while the B modes are rotated 45 degrees with respect to k. To visualize the polarization maps, E and B modes can be expressed as Stokes parameters Q and U. E and B modes are in both Q and U polarization maps. On the left here we see a Q map dominated by E modes, and we can see a vertical and a horizontal pattern present in the map. While on the right we see a Q map dominated by B modes, where the polarization pattern is diagonal, rotated about 45 degrees. Polarization maps must be masked to cut out poorly defined pixels or ambiguous pixels. But this creates a problem known as E to B leakage. Masking the map creates artificial B modes from E mode signals. This leakage mainly occurs at the edge of the mask, which can be seen in the rings in the images below. To visualize the leakage, I started from zeroing out B modes and applying a mask to the polarization maps that only contained E modes. The E modes are then zeroed out after the mask is applied, and the maps are transformed to QU maps. And we can see, if you recall on the last slide, the image to the right showed a B mode pattern in the Q map, and this is clearly the same type of pattern. There are current methods to fix the problem of E to B leakage, but they are computationally expensive. So our goal is to fix this problem of E to B leakage through a convolutional neural network, or CNN. The model is trained to filter out E-mode polarization. It attempts to change input maps that contain both E and B modes, expressed as Q and U maps, and filter out the E modes. The target data are also QU maps, but they contain only B modes. Convolutional neural networks are able to reduce images into a form that is easier for the model to process without losing important features, namely polarization patterns at different resolutions. CNNs pass information through layers where each layer performs an operation on the data. This is a diagram of the model I created using TensorFlow and Keras. Starting in the top left, we have input polarization maps. In this case, an example is an input Q map that contains both E and B modes. And it starts at a resolution of 576 by 576 pixels. Each arrow represents a new operation on the data and a new layer. It goes down to a resolution of 68 by 68 pixels while applying skip connections to retain the information at low resolutions. On the left side is the encoder path, and on the right side is the decoder path, indicated by red arrows for the encoder and blue arrows for the decoder. The decoder path upscales it until it reaches the desired output of 512 by 512 pixels. We can see the output Q map looks to be dominated by B modes instead of the previous E modes. Separate polarization maps were created that were not used during the training to test the effectiveness of the model. The prediction of the model was then compared to target maps. The correlation of these maps was measured where the ideal correlation between the maps would be close to 1, indicating the E modes were perfectly filtered out. And we can see the results are pretty good so far, where the correlation's reaching levels of about 0.8, and we really care about the correlation at low L values. So there's some ideas for the future that we want to try out and see if we can raise this correlation even higher and get this graph shifted slightly to the left so that we get a higher correlation at low L's. Now we can see that these different lines indicate data that have passed through the model a certain amount of times. So for example, E10 shows the amount of times that all the data passed through the model 10 times to train the model. So as you get to E of 100, that means all the data was used 100 times to train the model. Ideally, 100 training times means better results, but we can see the graph shifts down after about 60 training sessions. So we're looking at adding in layers to prevent overtraining. We're looking at adding new operations and adding additional layers to obtain information at lower resolutions to shift this multipole moment L to the left more so that we get a higher correlation at low L's. Thanks for listening and watching. I hope you have a good rest of your day.